After having learned about mass spectrometry, let's look at the coupling of liquid chromatography to mass spectrometry, abbreviated LC-MS. LC-MS and LC-MS-MS, which means tandem mass spectrometry with fragmentation, are most likely the most widely used methods in bioanalysis of complex samples. Here we see a typical setup from our own laboratory. On the right side, you see the Orbitrap mass spectrometer. It's actually a combination of a linear ion trap and an Orbitrap. And in the back, you see two HPLC systems, one for micro and nano flow on the right, and one for normal flow on the left. You can see that this is a fairly technical setup, although once you know how it works, it's all less difficult than what it looks like. If you're interested in projects in the lab, you're welcome to come by and take a look at the lab yourself. So let's take a look why the combination of LC and MS is so strong. It is mainly because the separation of the molecules is very orthogonal. That means separation in liquid chromatography and separation in mass spectrometry are based on completely different and unrelated physical-chemical molecular properties. In liquid chromatography, as you know, you can separate molecules based on ionic properties, charge, hydrophobic properties, their size or hydrodynamic radius, or the affinity to certain ligands such as antibodies or other affinity ligands. In mass spectrometry, as we've seen, you separate ions in the gas phase according to their mass-to-charge ratio, and you have the possibility for fragmentation to obtain additional molecular information. So taken together, this combination can be very, very powerful, very selective to analyze molecules in highly complex bioanalytical matrices such as blood serum or plasma. However, there are practical challenges to combine HPLC or LC with mass spectrometry. Because liquid chromatography works at atmospheric pressure with samples, molecules in solution, while mass spectrometry works under high vacuum with ions in the gas phase. What are the challenges then? We have to introduce solutions into a high vacuum. That means there have to be very efficient vacuum pumps that can remove all the other solvent-related molecules and maintain a high vacuum for the ions to be separated according to their mass-to-charge ratio. We need to supply heat, the drying gas, as you may remember, for evaporation of the solvent. This may lead to thermal degradation of the molecules. The ionization of the sample solvents and additives provides enormous gas load to the vacuum pumps. Additives also should be volatile. That means we are somewhat restricted with the mobile phases for HPLC. For example, in non-volatile buffers like phosphate buffers or borate buffers are pretty much out of the questions, as are detergents like SDS. Just to give you an example, 1 milliliter of eluent will produce 1 liter of gas at atmospheric pressure, but it will produce 1 million liters of gas at 10 to the minus 6 atmospheres. And as some analyzers work at 10 to the minus 9 atmospheres, that would be 1 billion liters of gas. If you now consider a classical liquid chromatography flow rate of 1 milliliter per minute, that means that 1 million to 1 billion liters of gas have to be pumped away every minute out of the mass spectrometer. This gives you an idea why a large part of the big box of the mass spectrometer consists of vacuum pumps. First, oil pumps that generate a primary vacuum of 10 to the minus 3 atmospheres, and then turbomolecular pumps that can reach 10 to the minus 9 atmospheres. This was for the longest time very difficult, if not impossible, and all kinds of tricks were used. Only with the advent of electrospray ionization and atmospheric pressure chemical ionization has the coupling of liquid chromatography to mass spectrometry become a routine methodology. One way to alleviate the pain a little bit is to go to lower flow rates, so-called nano-LC, which pumps at nanoliters, or better say hundreds of nanoliters to microliter per minute flow rates. That's already 1,000 times to 10,000 times less than with regular LC. However, scaling down the chromatography comes at a price, because you have to work with very narrow channels. Here is shown a microfluidic device which is used for chromatography, a so-called chip, an LC chip. You can see on the left the 6-port valve, which is classic and is needed for injection of the sample and also for removing waste. In the middle you see a so-called enrichment column. This traps the molecules that you would like to analyze while removing, for example, salts from the sample to waste. When the valve is switched, the enrichment column goes in line with the analytical column, which is essentially a packed 75 micrometer channel in the microfluidic chip, and the molecules are eluted with a gradient program through the analytical column and the spray needle via electrospray ionization to the mass spectrometer. So this is an online LC-MS system working at maybe 250 nanoliters per minute. The challenge is, if you work at such low flow rates and with such small channels, to have very clean samples. And clean doesn't only mean well prepared, but also clean, removed from particles, because every particle may block this channel and thus break down your analytical column system. It's a very sensitive technique. You can analyze very small sample amounts. For example, we've used it for biopsies or for tissue samples captured by laser microdissection. Sample amounts that can be detected are below 1 femtomole, that means 10 to the minus 15 moles. However, due to the miniaturization, this is not such a robust method. So if you have enough sample and you do not need this very low sample amount, like for plasma and serum from humans, you usually have enough. It is preferable to go to a little bit bigger system. We now routinely work with systems that work at about 3 to 5 microliters per minute and have channel diameters of about 300 micrometers or 0.3 millimeters. Here is an example of a nanoLC-MS chromatogram. You see on the x-axis is the retention time, the molecules coming out of the column, in this case peptides from a protein digest. And on the y-axis you see the ion current. That means the number of ions per time reaching the detector of the mass spectrometer. This is an MS run. That means there's no fragmentation. So if you would zoom in into the peaks, you would see that about at every maybe half second you have a mass spectrum which you can interrogate and see. You can see that even such a simple analysis with only a handful of peaks contains lots of data and thus generates enormous data files. Thus this relates also later to data processing, bioinformatics and the analysis of the data. So this is a very important part of mass spectrometry, especially in the proteomics and metabolomics area, which we will unfortunately not be able to deal with in this course. However, there are more advanced master's courses where we refer to these kind of challenges. I've chosen 3 examples to introduce LC-MS to you. The first one is the analysis of a biopharmaceutical protein, a monoclonal antibody, that should be analyzed in serum, a very complex protein-rich matrix. The second is work from my own group on the analysis of the cytokine trail, which is a protein that induces apoptosis in cancer cells. This protein was also analyzed in serum. Finally, I refer to very widely used analysis of metabolites in the clinic, the so-called Acyl-Carnitines. These are biomarkers for metabolic disorders in newly born children, and millions of analyses are performed every year around the world. Let's remember briefly what an antibody looks like. We've already seen this on the chapter on ligand binding assays. An antibody is made of 2 chains, a light chain, here shown in light green, and a heavy chain in dark green. These chains are linked together by disulfide bridges. there are hinge regions which can be cleaved. Further to this, antibodies are glycosylated on the constant regions of the heavy chain. So it's a very complex big molecule of about 150,000 Dalton, which needs to be analyzed in a matrix like serum, which itself contains a lot of antibodies. So how can you discriminate a pharmaceutical antibody from the lots of different antibodies that we already have in serum as it is? To discriminate the pharmaceutical antibody from other proteins in serum, and especially from other antibodies, we have to find a place in the molecules that is unique, a so-called signature or proteotypic peptide. What are the criteria for such a peptide? Well, first of all, it has to be unique for the protein of interest. So it should not occur in any of the other thousands and thousands of proteins in serum. How can I assure that? I have to look into the sequence database and align my chosen peptide with all the other possible peptides in the human sequence database to see whether there's any possibility that another protein contains the same amino acid sequence. Second, the chosen peptide should ionize well and give intense fragment ion signals. How can I determine that? That's quite difficult, but you can conclude some things from the structure of the peptide. For example, since we're using usually trypsin, the peptide should contain amino acids that can be positively ionized, such as lysine and arginine. There are also growing databases of actual experimental data that are collected. So if you're lucky, you can find your peptide in one of these databases, and you can see from experimental data whether it's a good or a bad peptide in terms of ionization. You choose one fragment ion for quantification, usually the one that gives the strongest signal, and two more for confirmation, because it is quite risky to base your analysis on one transition, as it's called. It means on one fragment ion, because there are so many proteins in the sample, and it can well be that there is an overlap with another peptide, even if the sequence is unique. So you have the so-called quantifier fragment ion and the two qualifier fragment ions. And finally, you add a stable isotope labeled internal standard for absolute quantification. This is usually the same peptide labeled with carbon-13 and or deuterium. These peptides can be acquired commercially, made by chemical synthesis, although they are usually not cheap. In the following, we make use of the triple quadrupole mass analyzer in a so-called selected reaction monitoring or SRM mode. What does it look like? Let's assume your complex sample of peptides is coming out through the nozzle out of your chromatographic column on the left, entering the first quadrupole Q1. Now you know which peptide you would like to measure. It's your signature peptide. So you select the ion corresponding to your signature peptide. This ion is subsequently transmitted into the collision cell, where it collides with nitrogen or argon and breaks into pieces, so-called fragments. And these fragments are analyzed in the third quadrupole Q3 and then detected. Each change from the m/c value of the precursor ion to the m/c value of one of the fragments is called a transition. You follow these transitions online with liquid chromatography to detect your peptide in the complex mixture. To quantify it, you also select the precursor ion of the stable isotope labeled peptide as internal standard and follow its transitions as well. By relating the intensity of these signals for the endogenous signature peptide with the added stable isotope labeled internal standard signature peptide, you can thus quantify your molecule, in this case a monoclonal antibody. Before doing so, it is of interest to look at the fragmentation pattern of peptides. It's actually not very complicated. The main fragmentation that you get by collisional induced activation, as we call this, what's happening in the collision cell, are two types of fragments, B and Y. The B fragments are the fragments coming from the N-terminus of the peptide, where the charge stays with the N-terminal fragment. The Y fragments come from the C-terminal part of the peptide. Naturally, you cannot break a bond without getting both fragments, as you cannot break a stick without having two ends, so you have two fragments. As the mass spectrometer can only work with ions, that means with charged molecules, it depends very much where the charge is localized and how intense the signal of a given fragment will be. As you can see, fragmentation occurs at the peptide bond, that means at the amide bond that links the amino acids together in the peptide. So in most cases you get a B-type ion series coming from the N-terminus of the peptide and a Y-type ion series coming from the C-terminus of the peptide. In the paper by Hödi et al. Cited below, this signature peptide was selected. It is fairly long, but is specific for a monoclonal antibody that was analyzed in a serum of a monkey in preclinical studies to measure its concentration after an injection. You can see it starts on the N-terminus with a threonine and ends with a lysine at the C-terminus due to the trypsin cleavage. Hödi et al. Selected two transitions, a transition to the Y8 and to the Y6 fragment. Remember, these are the fragments from the C-terminus of the peptide, which carry most of the charge due to the basic amino acid lysine. You can see the transitions in the mass spectrum below. From the doubly charged precursor ion M+2H2+, you have one transition, the quantifier to Y8, the most intense transition, and you have one transition, the qualifier to Y6. Hödi et al. Chose only one qualifier, although it is quite advisable to choose a second one to make sure you're really following the right peptide. For such an analysis in such a complex biological matrix, it is important to check the selectivity of your method. At panel A you can see a Planck serum which does not contain the therapeutic monoclonal antibody. Despite the fact that we use liquid chromatography and despite the fact that we use selected reaction monitoring, the sample is so complex that still signals are seen for the transitions chosen. This means that there are other peptides in the sample that give or overlap with these transitions. Remember, we're using quadrupole mass analyzers which are not high resolution, so we have a window of about 1 atomic mass units, so other transitions may just fall by chance into that window. It is important to have chromatography here to make sure that these peptides, the background, are separated from the peptide of interest. If you look at panel C, you see 5 microgram per milliliter of the monoclonal antibody added to Planck serum. While you can see that the background peaks are still there and somewhat changing, you can also see that there is an additional peak clearly visible. This is the signature peptide from the monoclonal antibody. So it can be quantified at that level despite the interferences of other peptides, and this is due to the chromatographic separation. You can improve the situation by doing some sample preparation. As we've heard in the beginning, sample preparation is extremely important for bioanalytical methods in complex samples. So here a solid phase extraction was done on a reversed phase cartridge. This has improved the situation somewhat, but as you can see, not a hell of a lot. I'm showing this as an example of a fairly poor sample preparation actually, because you might say it looks almost like Planck serum, despite the additional SPE step. So you could do better probably. In D you see the internal standard, the stable isotope labeled antibody in this case. Hödi et al. Were fortunate enough that they were expressing the antibody themselves. So they could label it completely with 15 nitrogen, and then doing the same digestion they get a 15 nitrogen labeled peptide, which is heavier As you can see, the doubly charged precursor ion is 10 atomic mass units higher than the one on panel C. The internal standard was added at a fairly high concentration, probably too high for real quantification, 227 microgram per milliliter, and at that level it's no problem at all to detect it. However, that's an easy example. As you will see later from our own work, when you go to the nanogram per milliliter level, things become a lot more challenging. So what about the actual use of such a method? Here it's used to determine the pharmacokinetics of this monoclonal antibody, and it's compared with an ligand binding assay, an ELISA, which is the classical assay so far. As you can see, the curves show fairly similar pharmacokinetic behavior, although the absolute quantification concentration levels are slightly higher with LC-MS compared to ELISA. This may be due to the fact that the ligand binding assay may be somewhat interfered with, for example, by other molecules binding to the monoclonal antibody interfering with the detecting antibody of the ELISA. There may be other reasons why this is different, and there has been work done to look into that. We've published a review recently, so if you're interested, I can pass it on to you. Let's look at a more challenging example from our own work. Measurement of the recombinant cytokine trail in serum. This requires a lot more sample preparation, as we would like to measure this molecule at the nanogram per milliliter level. Details can be found in the publication given below. After serum collection, we add the metabolically labeled, stable isotope labeled protein standard. Again, we were fortunate, since due to the collaboration with the group of Professor Quacks, we were able to express the protein in 15N labeled growth medium in E. coli, and we got a homogeneously 15N labeled trail protein. An important step was to use immobilized metal affinity enrichment to enrich this protein. Since trail has surface-exposed histidine residues, we reasoned that these residues should interact with immobilized metal ions such as nickel 2+. So you already see you have to look at your protein as your small molecular weight analyte, try to understand its physico-chemical properties and specific properties, and use them for sample preparation. With this simple solid phase extraction step, we could remove 95% of all matrix proteins from serum and recover 72% of recombinant human trail. Now we do a triptych digestion to release the peptides, including the signature peptides. Because don't forget, there's also trail in serum, endogenous trail. We add 15% acetonitrile prior to the digestion to denature the protein somewhat and to make it more accessible to the protease. Unfortunately, our signature peptide contained an unstable amino acid methionine, which has a sulfur. This sulfur can be easily oxidized to the sulfoxide, changing the mass by +16. Clearly, for mass spectrometry, this is something we do not want, because then we would not have one signature peptide, but possibly two. And oxidation is very hard to control, so you may have a lot or a little of +16 peptide. To avoid this problem, we devised a step where we would oxidize all the methionines to the methionine sulfoxide by adding a little bit of hydrogen peroxide and waiting 2 minutes. Now we're ready for the LC-MS analysis in SRM mode, following quantifiers and qualifiers. Here is a chromatogram of the analyses. You see 2 peaks. Why 2 peaks? Well, we do not only want to analyze recombinant human trail, which is the wild type on the left, WT, but also a site-directed mutant that was developed in the Quacks group to avoid interaction with unwanted receptors, so-called decoy receptors you may have heard of. This is the 4C7 variant. This variant differs by 1 amino acid from the wild type. You can see that serine in position 3, YTS, is replaced by aspartic acid, YTD, in the variant. This is very hard to discriminate with an immunoassay as you have only one amino acid difference. However, mass spectrometry has no problem because there are two properties that change. A, the retention time, as you can see the wild-type peptide elutes earlier, and the molecular mass changes. So it's easy for us to discriminate between the two. You can see the different transitions. You see the quantifier, Y8 plus on the left side and B3 plus on the right side for the variant, and all the two qualifiers underneath. It's very important that quantifiers and qualifiers co-elute exactly as they are derived from the same peptide. If this is not the case, there's an indication of interference maybe from other peptides in the sample, and this must be investigated. Indeed, this duplex LC-MS-MS method allowed us to quantify wild-type recombinant human trail and the variant recombinant human trail 4C7 at the same time in mice after an intraperitoneal injection of 5 mg per kilogram. As you can see, the concentration goes into the microgram per milliliter range, but at the end we are only close to 20 nanogram per milliliter. We can follow the entire pharmacokinetic curve with liquid chromatography tandem mass spectrometry thanks to the chromatographic separation of the two peptides and the selectivity of the mass spectrometer. Let's look at the last application, which focuses on the metabolites Acyl-Carnitines. These are well-known biomarkers for metabolic disorders in newly born children. There are millions of LC-MS analyses done every year to screen for metabolic disorders and to adapt generally the nutrition of these children to avoid long-term effects. First of all, let's look at the molecule. This is a typical acyl-carnitine. It has a hydrophilic head group, an amine, the so-called carnitine, and an acyl chain connected via an ester bond over here. This acyl chain, if we count it, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 C atoms long. It's a C16 acyl-carnitine. In the case of inborn metabolic errors, there are some enzymes missing to attach the fatty acid to the carnitine, and you will see certain acyl-carnitines missing in the spectrum. Since we do not know whether a child has an inborn error of metabolism, and if so, which one it is, we need to screen the whole family of acyl-carnitines. In order to do so, acyl-carnitines are first derivatized to their butylesters. If you remember, or you look back one slide, you see that there is a free carboxylic acid group which can be derivatized with butanol. This leads to a common fragment for all acyl-carnitines independent of the fatty acid of 85 atomic mass units. When you look at the precursor ion mass, you can then derive which acyl-carnitine it was, because if different fatty acids are attached, obviously the precursor ion mass will be different. We call this methodology precursor ion scanning. To do a precursor ion scan, we use the same triple quadrupole mass spectrometer, but in a different way. First we scan Q1. Remember, in selected reaction monitoring we had it fixed and used it as a mass filter to select the signature peptide. Now we scan quadrupole 1. We again have collision-induced dissociation in the collision cell to produce fragments. But in this case, we fix quadrupole 3 at the mass of 85. That means the radio frequency is fixed, that only fragment with the mass-to-charge ratio of 85 will go through and reach the detector. In other words, we look at all the molecules that produce a fragment ion of 85 atomic mass units. This is called precursor ion scanning. Here is an example of MS-MS spectra that explain this. It's octanoyl carnitine having a C8 fatty acid chain. On the top two layers you see the product ions of the endogenous octanoyl-carnitine and the deuterated, stable isotope-labeled internal standard. As the butanol group is not deuterated, the fragment ion is 85 in both cases. At the bottom we see the precursor ion spectra. Octanoyl-carnitine has a mass of 344, while the 3 times deuterated internal standard has a mass of 347 and thus can be discriminated from the endogenous molecule. Importantly for precursor ion scanning, both give the same product ion at 85, at which quadrupole 3 is fixed. Here we see a couple of spectra, MS-MS spectra, from the textbook of clinical chemistry and molecular diagnostics. On the top we see a normal spectrum with all the acyl-carnitines marked with stars. Panel B shows deficiency of transport, an enzyme that transports the C3 acyl-carnitines into the mitochondria. They thus enrich in the serum. So you see a big peak of C3 acyl-carnitine. The next we see a serum from a patient with C4 deficiency. As you can see, C4 is completely absent in the normal, but it's clearly visible in the deficient serum. C5 deficiency in the same way, you can see the C5 acyl-carnitine peak. C8 deficiency is shown next. Then we have the very long chain deficiency, which translates into a number of peaks appearing, the C14-1, C16-1 and the C18-1 acyl-carnitine. And finally the long chain deficiency, which results again in C14-1, C16-OH and C18-1-OH. You can see that the very long chain and long chain transporter enzymes are not as specific as the short chain acyl-carnitines, where only one peak occurs. Well, in the C8 you already see the C10-1, which I overlooked actually, and also the C6 a little bit, but in the end you see multiple fatty acid chain lengths occurring in the spectrum. First of all, you can already see that you don't have to be an expert to depict these deficiencies, as they occur as very strong signals on essentially zero background. This table gives an overview over all the transitions of acyl-carnitines. As you can see, they all result in the same fragment of 84.8, which I previously approximated with 85 mass to charge ratio. However, the mass of the precursor ions is different, but not in every case. You can see some pairs which are the same: 232, 246, 288, 261.9. In that case, it is really important to have the chromatographic separation, as otherwise these molecules could not be discriminated simply by precursor ion scanning mass spectrometry. Let's recapitulate at the end of this chapter. You've heard about ionization methods and the different mass analyzers in the beginning. The second part dealt with LC-MS, and remember the challenge to introduce large volumes of liquid into a high vacuum system needed for mass spectrometry. Finally, I introduced you to a couple of applications, also to exemplify the selected reaction monitoring SRM and the precursor ion scanning mode. These were the monoclonal antibody in serum, trail, and the acyl-carnitines to detect inborn errors of metabolism.